So today we are going to talk about the some other aspects of control system. Yeah. As I said before that in order to design a control system, first of all you have to determine whether the system is controllable or not, whether the system is observable or not. Now you all know the definition of a controllable system, right? The system is controllable if starting from any initial state x0, the system can be driven to any final state in some finite time, choosing the input variables, right? That's these are the things at your disposal. And it's a very practical problem, right? For example, an economist is trying to control the inflation of a country. So he has certain inputs in his hands, like the bank's lending rate, or money supply, or gross national products, all those things. So he wants to know how to manipulate those input variables to achieve the inflation, achieve certain rate of inflation in the country. So it's that as you can see, many instances we use this concept of contribution. Now, how do you test the contributive system? Well, as you can see from the definition, the contributivity is determined by the matrices, by the pair A and B. The output C doesn't have any role here, right? So the criteria of contributivity, mathematical criteria of contributivity, will be determined by the matrices here. So here are some well-known criteria of contributivity for continuous time systems. These criteria are mathematically equivalent, and they are of course mathematically correct. The first of all, the most well-known and very famous criteria of contributivity is so-called Kalman's criteria of contributivity, where you need to test whether the matrix B, AB, A square B up to the n minus 1B, which is called the contributivity matrix, right? Whether this contributivity matrix has full rank. Okay. What is the order of this matrix? How many rows and columns are there? How many rows are there? Nm by n. Okay, so there are other mathematical equivalent criteria, like this matrix is called the contributive Gramian. So the contributive Gramian has to be non-singular or any time t1 greater than 0. And there are quite a few. One of them is very important one. The rank of the matrix A minus lambda I B, this augmented matrix A minus lambda I B, has to be n for every eigenvalue A of the matrix A. Okay. Now, as I said, these criteria and other criteria will go along as we'll talk about as we go along. So the thing is this, that how good are these mathematical criteria from the computational point of view? That's the question we are asking now. So for that, let's look into the well-known Kalman's criteria of contributivity. Then more. Okay, so let's talk about the numerical test of controllability, right? Okay, so let's see how effective the Kalman criteria contributing is from the computational point of view. Well, to form the contributive matrix, B, A, B, etc. First of all, you have to compute different powers of the matrix A. Actually, you have to compute up to the n minus 1 power of the matrix A, which is a formidable computational task if A is of order say higher than 3 or 4. Okay. Second, you have to multiply each time by matrix B. And as I said before, that though it seems that matrix multiplication is a trivial task, computational task, but it is not. The multiplication of two matrices, when one of the matrices happens to be non-orthogonal, then there is a possibility that you will incur a huge amount of round-up errors. Okay? And that will cause the instability in the computation. Okay? And furthermore, even if you compute the contributive matrix quite accurately, then you have to determine the rank of that matrix, right? How do you determine the rank of a matrix numerically? We talked about it. How do you do it numerically? Non-zero singular values, yes. So we have talked about it, right? So you have to compute the singular values of that n by n matrix, nm by n matrix, and see whether the singular values are all different from 0. The number of non-zero singular values gives the rank of the matrix, right? Now, it might happen that some of the singular values are theoretically non-zero, but computationally 0. In that case, you will conclude the system is uncontrollable, even though theoretically it's controllable. Okay. So let's look into one example. Well, maybe I have to switch to my transparency because new stuff here. Can you switch my transparency? Is here? Is my hand? Is my hand? I have said it last time. ठीक है 616. Because, yeah, 616. On this ground. Okay, to illustrate the compositional difficulties with Kalman criteria controllability, let's look into this trivial example. You say A is a 10 by 10 diagonal matrix. Okay. And B is a single input matrix. That means it's just a components are equal to 1. Now you can easily see that this is clearly controllable. Now you have to form the contributive matrix B, AB up to the 9th power of B, and 9th power of A times B. Now since this matrix A is diagonal matrix, computing this contributive matrix is quite easy. Suppose you can do it and we compute the matrix, contributive matrix, and store it accurately on computer. Right. Then next you have to determine the rank of that contributive matrix, and you will see. I will ask you to do an example. I will ask you to do an exercise later in the class. That this contributive matrix has 3 small singular values of the order minus 10 to the 12, minus 9, minus to the 7, and so forth. So on a computer with machine precision no smaller than 10 to the minus 12, will conclude that the numerical length of this matrix is less than 10, implying that the system is uncontrollable. Though obviously, in your eye you can see the system is controllable. This because this system theoretically is controllable, but it's close to an uncontrollable system. That's the reason. And the Kalman's criteria controllability cannot predict that reason. So let's see what we can do. Whatever. And this type of remarks actually also hold good for other criteria controllability, because they are all mathematically. So for that reason, we have to think of some other numerically effective criteria control. Okay. What do you think we should do? We have to play with pair of matrices A and B, right? What do you think we should do? We have some tools in your hand, remember? There are 2 canonical forms that we can construct in a numerically effective way, in a numerically stable way. What are those? You are telling my language now. I'm so happy. Okay, so we have to see whether we can do that. Let's try to transform. But here one more thing. We have to work with pair of matrices here. So that means we have to have some way to transform the matrices A and B simultaneously to a form, Heisenberg form or real suit form, whatever it may be, in such a way that that form can be achieved in a numerically stable way. Right? Now it turns out that the process of transforming a matrix A to Heisenberg matrix that we have seen using household transformation can be easily extended to a pair of matrices A and B. There, the process was just on the matrix A, but that process can be easily extended. Okay, and as a result of that, what we'll get the following. Again, going back. So here is what I'm trying to tell you. Given the pair AB, we can always construct an orthogonal matrix P in such a way, there is an algorithm to do that, in such a way that PAP transpose is a matrix H, which is a Heisenberg matrix but in block form. So it's something called block Heisenberg matrix. I'll show you how it looks like. Okay. And at the same time, the matrix B will be transformed to a matrix B prime or B prime is such that it has a special form. Okay. So let's look into how it looks like. It's starting. So what I'm trying to say is the following. So given a pair of matrices A and B, there is an algorithm to construct an orthogonal matrix P such that PAP transpose is a block Heisenberg matrix. Now, how does a block Heisenberg matrix look like? What is a Heisenberg matrix except that it comes in block form? That means here there are block matrices on the diagonal, which are all square matrices, square block matrices on the diagonal, and non-square matrices on the subdiagonal. So here each term of the matrix is a block matrix. It's not a scalar. Okay. So the diagonal entries are all block matrices. Or square block matrices, and the subdiagonal entries are non-square block matrices. And at the same time, the matrix B can be transformed in the following form. And you will get it. So here how it looks like. You can look at that 6.7.2 here. That's how a block upper Heisenberg matrix looks like. So each of these blocks, H11, H22 up to HKK, each of these blocks is a square matrix. Okay. Of course, each of them is much smaller than n. And each of these sub-diagonal blocks, H21 to HKK minus 1, each of the sub-diagonal block is a rectangular matrix. And the matrix B is transformed to B prime, which has all of the following form. It is B1 at the top, some matrix, some non-zero matrix, and zeros everywhere else. Now, as soon as the pair AB is transformed into this form, you can easily determine whether the system is controllable or not. How? Well, it turns out the way the algorithm has been designed, I'm not going to the details of the algorithm, but you can the way the algorithm has been designed, that each of these sub-diagonal blocks is either a full rank matrix or is a zero matrix. Only there are two choices. Either each of the sub-diagonal block is a full rank matrix or is a zero matrix. Now, as soon if any of the sub-diagonal block happens to be zero matrix, then immediately it signifies the system is uncontrollable. On the other hand, if all the sub-diagonal blocks are full rank, then the system is controllable. This can be proven. And the algorithm to construct the orthogonal matrix P is a numerically stable algorithm. And the transformation from A to H and B to B prime, this transformation is an orthogonal transformation. So it's numerically stable. And this is how, in a computational setting, we determine whether a system is controllable or not. You understand the test? And the algorithm is called the staircase algorithm. That means it goes in different. It starts from the bottom and goes up and up and up. But for you, its most important thing is to know, you don't have to know the details of the algorithm. The algorithm has been coded in the MATLAB toolbox that comes with my book, Math Control. It's called okay. I'll give you the name of the MATLAB command to implement that has implemented that. Okay. Now let's take an example using this test. Let's take a numerical example. Okay. Here we have a pair A and B. Now we do about two steps of the algorithm, and then we arrive at this form. So this is your Bloch-Heisenberg matrix, upper Bloch-Heisenberg matrix that I'm talking about. This is your PAP transpose equal to some matrix H. We call it H because it's an recursive algorithm. So this is your Bloch-Heisenberg matrix, final Bloch-Heisenberg matrix, and your B matrix has this form. What could you say from here? Is the system controllable or uncontrollable? Controllable? Why is controllable? Look at great details. Uncontrollable. Why? Because this is a zero. So one of the sub-diagonal block, this sub-diagonal block of course is a scalar. It's zero. Okay. So this signifies the system is uncontrollable. Do you understand? Okay, let's take an example of a controllable system. Here is a 5 by 5 matrix, and B is a 2-input system. B has 2 columns. And with D, we go through the steps of the algorithm, and we arrive at the following. We arrive at, this is the final block of our matrix, H2. And your B prime has this block. So look into H2 and B prime and conclude if the system is controllable or uncontrollable. Okay, look into the block Heisenberg matrix. How many blocks are there on the diagonal? How many square blocks are there on the diagonal? 3. How many sub-diagonal blocks are there? 2. Do they have full rank? Yes. One of the sub-diagonal blocks is this one, right? Yeah. There's a pointer here, right? Yes. Okay. So one of the sub-diagonal blocks is this one. This 2 by 2 matrix here. Okay. And it's a 2 by 2 matrix. Its determinant is different from 0. Because both, it's an upper triangular matrix, both the entries are different from 0. So determinant is different from 0. So it must be full rank, right? You don't have to really apply singularity composition here. Normally you will use that, but in this case it's trivial. So it has full block. And what about this one? This one. This is also different from 0. This is scalar. This is different from 0. Right? So I have 2 sub-diagonal blocks. Both have full rank. One is 2 by 2 and the scalar. Both have full rank. So what could we conclude from here? And the B has this form also. Right? So what could we conclude from here? System is some people are talking. Are there any doubts? Do you understand what I'm saying?
Please repeat your side. Will you please repeat that?
What?
How do you find controllability in that matrix? Checking rank of the sub-diagonal blocks now.
Right.
So I'm not getting. How do you check that?
Okay. What are the sub-diagonal blocks here? What are the diagonal? How many diagonal blocks are there?
3.
3. And what is the dimension of each of the blocks?
2 by 2. That is 2 by 2.
2 by 2. How many sub-diagonal blocks are there?
2.
2. So this is one sub-diagonal block. This 2 by 2 matrix. This is one side of sub-diagonal blocks, and this is another one. So you see, this is one diagonal block. This is another diagonal block, and this is another one. Right? This is the second, and this is third. You get it now? So there are 2 sub-diagonal blocks, and both have full rank. And if you want to know whether the algorithm, there is an algorithm, I didn't show you the algorithm, is kind of complicated. The algorithm to construct this form. By the way, this form is called controller Heisenberg form. Transform this form, the form H, so all this is here H, and this is called B prime. Okay, the form H B prime, is called controller Heisenberg form. So the numerical test of controllability is that transform the pair AB to controller Heisenberg form and see if the diagonal blocks, if the sub-diagonal blocks have all pulled down. If any of them happens to be zero block, then immediately conclude that it's not controllable. Otherwise, the system is controllable. Yes.
The block Heisenberg form, you told all the diagonal blocks are square matrices, and
yes.
sub-diagonal blocks are non-square matrices.
Not square or square. It could be not square or square. But the sub-diagonal blocks can be square or not square. In this case, square. But the diagonal blocks are always square. But they don't necessarily mean that they will be all of the same order. They can be different orders. One can be order N1, one can be order N2, and so on and so forth.
It may be scalar.
They can be scalar, yes. But in the sum of all those N1, N2, will be equal to N. Okay, so now suppose your control input is just one. That means we have single input system. How will the test look like in that case? If it's a single input system, how will it look like? That means if your M is 1, that means B has one single column, right? Single input system. How will it look like? In that case, the block Heisenberg matrix will be just a scalar Heisenberg matrix. And the matrix B prime will be just a vector. Right? So in the single input case, in the single case, the matrix A will be just a scalar Heisenberg matrix, and B prime will be a vector of this block. And when will we then say that that single input system is controllable? When do we say that? It's a special case of the block Heisenberg form, right? Special case. Or block Heisenberg is the generalization of this case, right? So when would you say that the single input system is controllable?
Scalars are non-zero.
It will be controllable if all these sub-diagonal entries, which are scalars in this case, will be different from 0. That's it. If any of them happens to be 0, then the test is that, this conclusion is that system is controllable. So we'll in your tutorial today, we'll give you some examples to test. Okay. Any questions so far? The only thing I need to tell you how to construct this, how to construct this pair. And this is kind of complicated, but it's an extension of the householder's method. But actually, I don't expect you to know this at this stage. All you have to do, no, good thing is that I have implemented this thing in my control toolbox. There is no method, math control, I'm sorry, what they call it.
What does it do?
Yeah, MATLAB toolbox. I mean, MATLAB control toolbox, there is nothing. Yeah, there is a function called CNTRLHS, control agent platform. So probably can it be they can use this
Yes,
in the
yes.
tutorial.
I will give the rules.
So probably in the tutorial today we'll use this thing on some examples to see how it goes. Okay, understand what I'm saying? The course of day is going to give you those scores. Okay? He has the toolbox. He has the CD. So you have to just
I downloaded it.
okay.
You just write down the code. What is written here? You get the code in the email. What is the command that you will have to use to create this?
Oh my God.
इसका power का है. What's the power of this one? Just switch off that power. Switch off that power. No, these are gone. These are gone.
He do not touch. But very often you see on left the room. Okay, so the next is observability, right? So you know what is when the system is observable, right? Right? So what happened?
Came.
Okay.
So the observability is a dual concept of controllability, right? You know when a system is observable. The system is observable if the initial state x0 can be uniquely determined in finite time, okay, from the knowledge of the input and the output in a given range of time. So actually the observability is determined by, by the pair AC. The input matrix B doesn't have a role here, okay? It's determined by the pair AC. And the analogous criteria to Kalman's criteria controllability for observability is the following. Let me write down. Can we go to this page so that I don't have to write it?
To be
Six point. Or I will go up and I will go. Yeah, this one. So analogous to the theoretical test of controllability, there are tests of observability as well. The same type of test. So the one that is analogous to Kalman's kind of controllability is this matrix. That this matrix we call the observability matrix. This matrix will have to have full rank. So the matrix is the observability matrix is constructed out of matrices C and A. So write down the matrix C times A, C A square up to C. So this is called the observability matrix, and it has to have full rank. Now, again, if you to use this thing in a use this test in a computational setting, we might have some problems. Okay. So we can have a similar. We can have a test, a computationally effective test, similar to the one that we just saw for the controllability test. So the analogous test will be the following. 6.7. So here, in this case, we'll be working with the pair AC instead of AB, and we can again show that there exists an orthogonal matrix O, such that O transpose is a block Heisenberg matrix again of the same form, and the matrix C. Here you have to C is a matrix of this type, right? B is a long and thin, and C is how do you call it? This way. So C prime will be of this form. And the same test, the pair will be observable if H is a block unreduced, that means all the sub-diagonal blocks are full rank, and this matrix C1 has full rank. The same, it's analogous test. And again, the same algorithm which we use for the pair AB can be used for the pair CA to achieve this form. Okay. So we call this the block observer form, like the other one called block Heisenberg form, block controller Heisenberg form. This is block observer. And the test will be the same. The system will be observable if each of these sub-diagonal blocks has full rank. Okay. And the pair, as I say, is called observer Heisenberg pair. So I do not, in the single repeater, same thing. H will be as the scalar matrix in the single repeaters. And if all the sub-diagonal entries of the scalar matrix H are different from 0, and C1 has this form where C1 will be different from 0, then we say that the pair is, the system is observable. It's a dual concept. Now, as you can see that controllability or observability are determined basically by the singular values, because we have to determine the rank, right? The rank is determined by singular values of the controllability or observability matrix, right? Because remember, somebody was asking whether these two tests are equivalent. They are not equivalent. Basically, that we are decomposing the controllability matrix or the observability matrix in some special form. Okay. So question arises that if we do that, if singular value determine whether a system is controllable or a system is observable, then question arises that if some of the singular values are close to 0, that immediately tells us that the system is near an uncontrollable system or near an unobservable system, right? So in practice, sometimes it may be more important to ask whether the system is near an uncontrollable system, or the system, or whether a controllable system is near an uncontrollable system. Okay, or same thing for observable system. Like we are saying, instead of asking whether matrix A is non-singular, it's more important to ask whether matrix is a non-singular matrix is close to a singular matrix. Whether matrix A has full rank, instead of asking that, it's more important to ask whether a full rank matrix is close to a rank deficient matrix. Okay, and so there is, so we can talk about distance to an uncontrollable system. How a controllable system is how far a control system is from an uncontrollable system. Well, this is so again, we can give a simple example to show that what I'm saying has some meaning. Suppose you take this matrix A and the pair B, and you can easily see because this is a can you easily see that this is a controllable system? Or not? Is this a controllable system or not? Why it is controllable system? Yeah, it's a Heisenberg matrix. There is no square. It's a scalar Heisenberg matrix. All the diagonal entries and all the sub-diagonal entries are different from zero. Okay. And the met B has this property, or not all integers B are zero. So it's immediate that this matrix is controllable. And this system is controllable. Now, if we add this number minus to the 1 minus n, minus to the 1 minus n, minus to the 1 minus to the last row of the matrix BA. And you will agree with me that if n is large, then this number, 2 to the 1 minus n, is small number, right? Very small number. So that means if we add this a vector of very small numbers to the last row of BA, then you can probably do that in the math now. If you do that today, we can immediately see that system is uncontrollable system. So as I said, in practice, it is important to ask whether a controllable system is close to non-controllable system. And how does one determine that? So that means we have to have some measure of distance of a controllable system to a non-controllable system. Some measure of distance measure, right? And this is a kind of, it's not an easy concept, and it's quite involved mathematically. I'll just give you a flavor. I won't be able to go into details of this. But for all practical purposes, you don't have to worry about this. These things are more of mathematical nature than practical. You don't have to really worry much about it. Because you see, most of the systems that we encounter in practice, they are not as bad as it looks, and as I'm showing you here. They are really not that bad. Mathematicians always look up some examples to show some mathematical tests are bad, but it's not always right. Everything was so bad, everything what is being done in practice would have lost. Building would have lost, bridges would have lost, but it's not. Actually, the mathematician Wilkinson, remember the Wilkinson matrix, who came up with that matrix to show that how the eigenvalue system can be administered. He acknowledged that most of these systems that arise in practical applications in mechanical and electrical areas, and in most of the electrical and mechanical systems are not equal. Most of them are not. Okay. So you really don't have to worry much about that. But it's good to know that things can go wrong sometimes. But in most practical applications, you don't have to worry about these things. So the distance to uncontrollability is a number called mu AB. It is defined as follows. It's the minimum of all paired perturbation delta and delta B, such that the system defined by the perturbation delta and delta B is uncontrollable. Minimum of all perturbations. That means it's a minimum of all perturbations to the matrices A and B, which will make the system uncontrollable. It's a logical definition, right? You have a controllable system, put some perturbation, and you have to see whether the perturb system is uncontrollable. So you keep, you have to talk about the minimum of some perturbation. I can make a large perturbation, you can make small perturbation. So I have to talk about minimum perturbations that will make this system uncontrollable. And that is a number. The number, again, the number is not very easy to determine. And we can characterize the number in terms of the singular values, in terms of the smallest singular value. Because remember, the smallest single value is the one that measures whether a matrix has full rank, or I mean how close a full rank matrix is to a rank deficient matrix. Okay. So again, the same idea here. Here we are working with a pair instead of one single matrix. So the characteristic is the following: the distance to uncontrollability is defined as minimum of the smallest singular value of all perturbations of this problem, Si minus AB, where S runs over all complex numbers. So for each complex number, you form the matrix A, complex number S, you form the matrix Si minus AB. Okay, compute is minimum singular value. Okay, remember Si minus AB for a given S will be a rectangular matrix, but we can compute the singular value rectangular matrix, right? The singular value, they don't have, and the singular values are defined for rectangular matrix, in general. So we have to take the, for each of these matrix Si minus SIA, Si minus AB, there is a smallest singular value, right? And then you have to take the minimum where S runs for all complex numbers, and that minimum will give you the distance to uncontrollability. This is a sophisticated mathematical definition. But how do you implement this in practice? It's not that easy. You cannot test for all S's in the world. There are infinitely many. Right? So there are some tests to determine this number, and some of them are not really that good tests, but there are some numerical tests. But I will not bother you with those things. But it's enough to know. But there is something called distance to uncontrollability. It's a number determined. It's a number characterized by the smallest single values of certain matrices. Okay, that's enough for you to know. Okay, so I will probably skip that because you can see that some of the algorithms are so complicated. But if you are really interested, you can look into the book. Okay, probably now I'll go to the next section. The next section will be, yeah.
Sir, actually, when we are trying to look at this system is observable, actually what we are actually observe the system, practically what we are drawing the conclusion that the system is observable. So what is actually practically what we are observing in the system?
I don't understand.
What is the meaning of observable practically?
I told you the definition, right? That you have to see whether the initial state can be immediately determined from the input and output at a finite time. Okay. So you are trying to observe the minimum state, initial state. You are trying to observe in terms of the input. You are trying to observe the initial state. Can you determine the initial state immediately? Because you have a system, initial state is given. That may not be unique. But unless the initial state is unique, you cannot you cannot determine the state of the system, because any state x of t at a given time t depends on the initial state. So initial state has to be uniquely determined. Otherwise, for different initial state, you will get the different states. So when can you do that? If you are able to do that, then the system is observed. You understand? We'll talk a little bit about this when we talk about the design of observer. That's why something called design of observer. Because in many, we see that in many situations one cannot measure the state vector accurately. I mean, some of the components cannot be measured. So in that case, we have to design an observer. And the system has to be observable, otherwise it cannot design an observer.
Sir, is there any possibility or any algorithm to get a controllable system from an uncontrollable system?
What?
Sir, is there any possibility or any computational algorithm to get a controllable system from an uncontrollable system? Can you make a uncontrollable system
Can
a
you
controllable
make an
system?
uncontrollable system a controllable system by mathematics?
No.
Physical system, how it can.
Well, you can put some perturbations in the system, but you have different system. For example, if a system is uncontrollable because it has some, the contributing matrix has some small singular value, right? So you can put some perturbations in the system. The system will become controllable. But then you are not talking the same system. You are talking a perturbed system. That's it. There is no algorithm. You can do that. You have to actually what you have to do. You have to adjust the singular values, but then the whole thing will change. You talk a different system. But if a system is uncontrollable, because some modes are not controllable, because controllability sometimes is different in terms of the eigenvalue also, and then you can just eliminate that mode from the system. The system will be controllable. Okay, so we'll go to the next section, which is a very important thing. We'll talk about the stability of the system, right?
Which chapter?
Yeah, just say. Let's go. So we all know when a system is a stable system, we talk about stable system all the time, right? I mean, here we are talking about autonomous system without knowing. If there's an input, you can always manipulate the input to make this unstable system stable. So let's talk about the stability of an autonomous system, right? Now, so basically, we talk about the we talk about the asymptotic stability, right? The system is asymptotically stable if you make a small perturbation from the point of equilibrium. The system returns to the equal place, right? If it's so, then God the system will just that is as it will be. Now, how to determine whether the system is stable? Well, there's a well-known and classical mathematical criteria that says the system is controllable if and only if all the eigenvalues of the system matrix A, I'm sorry, of the eigenvalue statement A, have negative real terms. It's a very well-known mathematical criteria. And it's very classical. All the eigenvalues have to have negative real terms. Even if the matrix A is real, the eigenvalues may occur in complex quantum pairs, right? So all the eigenvalues have to have negative real terms. It's even on this statement. Now, long time before the computer era, the people did not know how to compute the eigenvalues for matrix A. It was as you say, if you try to compute the eigenvalues for matrix A from the characteristic polynomial, it will be, I'm sorry. So, if you try to determine the if you try to determine the roots of the characteristic polynomial, I mean determine the stability by finding the roots of the characteristic polynomial, there are some numerical properties. But people did not realize that. There are hundreds and hundreds of papers written on the stability criteria of the system based on the stability of the characteristic polynomial. Like you have all read about Routh-Hurwitz criteria, Routh criteria of stability, Deep's criteria, all those criteria, classical criteria. There are hundreds and hundreds of papers written. But the main point they missed here that that how to compute the characteristic polynomial first of all. The process now if you have a if you start from a control canonical form, of course the coefficient characteristic polynomial are there. But if you start from state space matrix A, full matrix, then how to compute the coefficient characteristic polynomial? And you have seen that process is numerically unstable. Well, there is so the people did not understand this very well. Also, it's a also there is a classical theorem by Lyapunov. All of you have heard about it. Lyapunov's theorem, right? The theorem, is a fundamental work in the theory of stability. But that theorem was not, of course, proved in the context of stability of a linear control system, linear system. That theorem was proved in context of stability of nonlinear systems. But if you use the theorem, people have used the theorem in the linear case, where the criteria is the following: that the matrix A will have negative real parts. I mean, the eigenvalue will have negative real parts, if and only there exists a symmetric positive vector in matrix X that satisfies the Lyapunov matrix equation. Okay. So this is the classical criteria of stability via Lyapunov matrix equation. Okay. And again, there have been hundreds and hundreds of papers have been written on the solution of the Lyapunov matrix equation, based on the fact that the system is controllable, and that one can compute the controlled canonical form of the system, which is nothing but the component form. They all miss the very fact that the controlled canonical form cannot be computed in a numerical stability, numerically stable way. Okay. But this equation, the Lyapunov matrix equation, is a fundamental contribution to control system linear analysis. We'll see even for the linear control system, there are many applications where one needs to solve routinely this Lyapunov matrix equation. So, how to solve it in a computationally effective way, not by transforming the matrix A to a companion matrix. That cannot be done. So we have some stable algorithm to do that. We'll talk about it a little later. But as you can see, that this will not be an effective test of stability, effective practical test of stability. Why? Because it turns out, in order to solve the Lyapunov matrix equation in a numerically effective way, you have to transform the matrix A to real suit from the matrix. That can be done in a numerically stable way by using keyword retrieval algorithm. And if you have the real suit from the matrix, then you can see the eigenvalue there, right? And that will be much more expensive than finding the eigenvalue itself sometimes, because once you have the real suit form, then you have to solve this matrix equation. Then you have to determine whether the solution is positive definite or not. So as far as Lyapunov matrix equation is concerned, to test the stability of system, it is counterproductive. Okay. Lyapunov matrix equation is a fundamental contribution. We need it for some other control purposes. But as far as stability is concerned, this is not practical thinking. Okay. So what do you do in practice? In practice, in order to test the stability of a system, you just compute all the eigenvalues. That's it. By using the keyword retrieval algorithm. And mathematics can do it in microseconds. Just say I of A, in microseconds you get all the eigenvalues. That's it. But as I said before, let me repeat that this equation is an important equation for many important tasks of control systems in general analysis. And we have to know how to solve this equation. We'll see some applications.
Now, there are certain systems where eigenvalues are infinite. So are there any numerical methods by eigenvalues of some systems, or representative eigenvalues of some system, for where we can talk about the stability?
I can know the
Like delayed system. Has any work been reported in that direction numerically?
This is transcendental problem. And all these computations are finite. So unfortunately, challenging area, I don't know. I don't know. Okay. So we'll talk about talk about a numerically effective way to solve the Lyapunov matrix equation later. There are a lot of theory on even for the Lyapunov matrix equation in the linear case. So here are some of the results. Like remember that these matrices are called contributive Gramian and the observability Gramian, right? And one of the tests of contributivity is that the contributive Gramian has to be positive definite. Okay. Similarly, one of the tests for observability is that this observability Gramian has to be positive definite. Now, how do you compute these two Gramians? Because if you have to compute this from the definition, you have to compute the exponential of the matrix A, and then you have to take the integral. It can be done, but it's a very involved process. On the other hand, it can be shown that the continuity in observability can be computed by solving a Lyapunov matrix equation. So there is a relationship between the continuity gameon and the Lyapunov matrix equation. So look at here 7.2.0. It says suppose A is a stable matrix, then the continuity gameon satisfies the Lyapunov matrix equation and is symmetric positive definite if and only if the pair AB is controllable. So the right hand side of the Lyapunov matrix equation is of the form B transpose, but B is the control input matrix. And the theorem says that if A is a stable matrix means it has all its eigenvalues have negative real terms. Sometimes in control theory also you have seen the term called Hurwitz matrix from the Hurwitz criteria of stability. So Hurwitz matrix also means a stable matrix. Stable matrix means now the stability is different than numerical stability. We are talking about asymptotic stability, right? So stable matrix means that all the eigenvalues are negative real terms. So the first criteria says if the matrix A is stable, the continuity gameon CG satisfies the Lyapunov matrix equation of this form. And this solution CG is symmetric positive definite if and only if AB is controllable. So this is a way to test the controllability of the pair AB where A is a stable matrix. Okay. So you have to know how to solve the Lyapunov matrix equation. We'll talk about that later. And the similar result holds for the observability gameon. It says that AB is a stable matrix, then the observability gameon OG satisfies the Lyapunov matrix equation. So instead of B transpose, now we have C transpose C. And again the same thing, the solution, the gameon will be positive definite if only A is of them. So this is another way to determine the observability of the system when the system is stable. We'll see that these things are important, right? We'll see that later. And there are some examples. You can see the examples. And I said this is a small but trivial example. Suppose the matrix A. This matrix is of course stable matrix because all the eigenvalues are -1, -2, -3. It's a stable matrix. And of course we can see easily that okay. So now in order to see if the pair AB is controllable, what we can do, we can solve this Lyapunov matrix equation. And the solution we get, there is a method common called Lyap, L-Y-A-P, that solves the Lyapunov matrix equation. But how it is done, we'll learn about it later. So if we just solve this Lyapunov equation using method common Lyap, at this point you should use Lyap because I've not told you yet what is the numerical algorithm behind Lyap here, but you can use it for the time. So if you using the method function Lyap, we can compute the matrix X as follows. And this matrix is clearly non-singular. I'm sorry, clearly singular. So the conclusion will be that AB is not controllable. As a matter of fact, you can see if you do the controllability matrix CM, controllability matrix B, AB, S square B, if you form the matrix and compute the singular values, you will see that one of the singular values is 0, signifying the system is not complete. You can use the controller Heisenberg form also. The block Heisenberg form. So these are some of the what I'm trying to say here. Well, I'm showing you some applications of Lyapunov matrix equation. With a comment that Lyapunov matrix equation is no longer a computationally viable criteria for testing if the system is stable. But we need to know how to solve this equation, because there are many control applications where Lyapunov matrix equation plays a very important role. This is some of the examples. There is something called H2 norm, HUD norm, but we'll talk about that later. So these things also, computing the H2 norm also requires the solution of the Lyapunov matrix equation. Now, we did not talk about the discrete type system, but discrete is an autonomous discrete type system. Again, this most of the results that we are talking about also hold good for discrete type system also. For example, in case of stability of discrete type system, instead of saying all the eigenvalues are negative real parts, we'll be talking about all the eigenvalues are inside the unit circle. So a discrete time system is asymptotically stable even only if all the eigenvalues are inside the unit circle. And then again also there are some classical tests by Su. Okay. You test the stability of this. Again the same remark applies. Test the stability of discrete time system also. All you have to do to compute all the eigenvalues and see whether they are all inside the unit circle. There are discrete time Lyapunov equation also, which is of the form x minus a transpose x a equals some matrix A. In the continuous time, this the matrix equation is x a plus a transpose x equals some matrix. The discrete time, the matrix, the Lyapunov matrix equation x minus a transpose x a equals some matrix. And again, we'll talk about how to solve a discrete time Lyapunov matrix equation in a numerically stable way. Okay. Okay, there is just one more thing I'll talk today and then we'll stop. That is distance to we talked about the distance to an uncontrollable system. The same type of concept, distance to an unstable system. That means question is how nearly unstable is a stable system. Okay. So again, there's a simple example to show that a perfectly stable system can be very close to an unstable system. For example, this is a matrix A. It's a triangular matrix with diagonal entities are all equal to minus 0.5. So it's perfectly stable. The eigenvalues are all minus 0.5, perfectly stable. However, if you perturb the sixth one entry, this entry, with small numbers, say it's 1 over 324. So this number from 0, if you perturb this with small number and recompute the eigenvalues of the matrix, then see that some of the eigenvalues, one of the eigenvalues become 0. Others have all negative real parts, the one of the eigenvalues becomes 0. Showing that this stable system matrix or the stable system is very close to an unstable system. A small perturbation makes this stable matrix an unstable matrix. So again, so one can talk about the distance to instability, right? For a stable system is close to an unstable system. What sort of perturbation needed to make a stable system unstable system? And again, as you can see, the singular values will give you the answers. That's why I talked about singular values so important. So, like the measure of uncontrollability and measure of distance to uncontrollability, we can also define a measure of distance to instability. So, distance to instability again is defined in terms of the singular values, like here. Beta A is defined as a distance to instability, it's a number that is defined as minimum of all the smallest singular values of the matrix A minus J omega I, where omega runs over all the real numbers. Okay. Again, the minimum singular value plays an important role. So you understand the definition of this thing. For every omega, real omega, you have this matrix A minus J omega I, right? J is minus square root of minus 1. Right? The electrical engineers, in mathematics, we use I, but in electrical engineering, we use J, because I stands for the current, right? So J is, square root of minus 1. So for every omega, the A minus J omega I is a matrix, and you can compute all these singular values. Take the minimum singular value, okay? And then you take the minimum of all the minimum singular values for all omegas. Okay? When omega runs for all over the real numbers, then that number is defined as the distance of instability. And you can see that it's kind of complicated to compute the number. So again, you don't have to worry too much about how to compute the number, because all is important for you. You know that there are cases where the systems, perfectly stable system, can be close to an unstable system, but those are rare practical cases. There are not many practical systems. But there are some tools to determine whether a perfectly stable system is near an unstable system. Yeah. Actually, again, the Lyapunov matrix equation can be used to determine some bounds of this number. You cannot compute the number. The Lyapunov matrix equation can be used to obtain some bounds. I tell you, I'll show you one later. Just as to show you that how important Lyapunov matrix equation is. Yeah, distance to an unstable system and Lyapunov matrix equation. Suppose A be a complex matrix, is stable, and let X be the unique positive Hermitian definite solution of the Lyapunov matrix equation, where M is a Hermitian positive definite matrix. So we are talking about complex numbers. So harmonic sample. Then if you compute this, the number beta n can always be shown to be greater than or equal to lambda mean of n. That means the lambda mean of m denotes the minimum eigenvalue of the matrix M. Even for the matrix M is positive definitely. That means all its eigenvalues are positive, real and positive. The positive matrix, positive definite matrix has all its eigenvalues positive. So all the eigenvalues of the matrix M are positive. So we can talk about the minimum of all the eigenvalues of the matrix M. So lambda mean M is the minimum eigenvalue. So we can show that the distance to instability is always greater than equal to the minimum eigenvalue of the matrix M divided by 2 times the 2 norm of the matrix X, which is the solution of this Lyapunov matrix equation. So again, it shows that Lyapunov matrix equation is so important in control application. We can now this theorem does not give you the beta of A as such, but it gives you some bound. Okay. And there is an example here to show you. Let's see. Very small example. The matrix A, again you can see that it has eigenvalue -1 and -0.0001. That means the matrix A is stable theoretically, but it's very close to an unstable system, right? Because there is one eigenvalue very close to 0. And you take the matrix M equal to just an identity matrix, solve the Lyapunov matrix equation. The Lyapunov matrix equal to of this X should be 1.5.5.5.9999.5. And if you compute the beta A, then it shows that beta A, that means distance to instability, is greater than or equal to the number 5.0002 times 10 to the minus 5. In fact, if you perturb the matrix, so beta A is the measure of distance to instability, right? And you can very easily verify that if you perturb the matrix A by that number, uncertainty of course, then one of the eigenvalues becomes 0, making it unstable. So it shows that beta A is a good measure, and therefore matrix equation can be used to measure, to give and bound that number.
So the question is, the solution of X, Lyapunov matrix is not unique, not to be unique.
This is unique, yeah, because A is stable matrix, and M is positive definite, so it's unique. It's a unique positive definite matrix. The solution is unique because A is stable.
What he is saying is you have started your solution with an assumption that AB is I2. AB is I. I did not take A equals to I.
Lyapunov criteria says that your A is stable matrix. If you look at the theorem, yeah, let A be a complex stable matrix. It's a stable matrix. So if A is stable, then X should be, Xa plus A star X to the minus M, but M is also positive definite. That solution X will be unique and positive definite. This will give a unique solution.
But the choice of M
has been positive, any positive
any
definite
positive
matrix.
or any positive,
Any
does
positive.
it hold that X will be unique.
For a given M,
For a given.
for a given M, which is positive definite X will be unique.
Of course, but for any
For any
The
n,
statement
for
is
any n which is positive definite, x will be unique.
X will be unique.
Yeah.
The X
All
that
n.
has been shown here, the projected here, can have a different choice.
What do you mean by that?
Sir, all n, not any n, for all n.
No, for any.
The X that you have selected
Yeah.
to show or to measure
I
the
didn't select
feature,
x comes out of the solution of the requirement sequence. I didn't select it.
but you have selected some M.
Yeah.
So now I change my selection of M.
Yeah. Then
Right.
still you get it.
I get a different value of X,
Yeah.
which is unique,
Yeah.
which may not be same as what has been shown here.
Yeah.
So in that case, the bound remains the same or different.
Only the same. You can. This is a good question. Why don't you do an experiment? See what happens. Let's do that in the tutorial today. Do an experiment. Yeah, I know this is a good question. I didn't think about that. It's a good question. Let's do an experiment. See what happens. I believe it will.
So the number that we are finding, distance to instability, it's just a mere number to know that how far we are from instability.
That means actually this number says that if you perturb that matrix A, stable matrix A, by the number times identity, then that matrix will be unstable. That's what it says.
But is it
But there are many such choices, but beta, the number beta is the unique choice, is the minimum one.
do we have any possibility to change that number to make our system stable?
Yeah, you can always do it. You can always construct a number, but the beta is uniquely determined by unique details. The definition of beta is here given. The measure of distance instability is unique. But you can do, you can make any perturbation to make an unstable system stable, a stable system unstable.
Because we do have
But
a
the question is, what is the minimum perturbation that you can make to make a stable system unstable? That's the question we are talking about. Any other question?
I have two questions.
Sure.
The first question is, can we visualize this one to be a measure of relative stability?
How to define relative stability?
Relative stability is in terms of eigenvalues. We say is how far they are from the multiple axis. They are more left, they are more stable, relatively more stable. So this could be visualized to be
Yeah.
number one. Number two, that you started with an A is a complex table. So far as mathematics is concerned, it's fine. The question is, can you please give example of physical system where system matrix comes out to be complex?
Well, most of the practical systems are not complex. Okay. But it works for the real matrices also.
It's a general
It's
case.
a general case.
Practical systems.
Are always real systems. There are some complex systems which can be made real immediately. But for all practical purposes, systems are real systems, of course, because it's a real world. But sometimes the data, when it comes from some experiments, it comes with some noise that looks like the system is complex, that can be figured out. Everything here works. But it's a mathematical case.
Some examples do have a matrix which are complex. Their system matrix is to be complex. Control. As far as we deal with control, we are but the same literature, the same algorithms, when it goes to communication, they are developing a channel matrix, a random channel matrix to different. So they don't use transpose. Mostly you'll find their literature with all arbitrations. And stability, also when they check, they deal with the complex matrix. They are mostly Hermitian and complex matrix. So because they deal with electromagnetic waves, they have both of them. And their type of modulation they do in the signal ultimately turns out to be complex. They work mostly with the complex matrix. But in our control, mostly we are never bothered about complex. We always do.
They use transports.
I think origin and reaction is clear about complex. Okay, we're done for the day.
Yes. Thank you. So we meet at what time? 3 or 5? 4? What is comfortable for you? 4 o'clock.